Welcome back. Today we will discuss about nice system optimization consisting of a wind park, a storage unit and a transmission unit. This is provided by a research group from the Princeton University in the US. So first is why we need storage. So we want to make wind dispatchable. We want to boost the wind capacity factor because sometimes the remuneration and the tariff is depending on the capacity factor. And we want to exploit high quality but remote wind resources. This is shown here on the left in the United States. In the Midwest, there's a lot of wind, but it's far away from everything. And therefore, transmission costs play a high role, and therefore they are considered here also for optimization. Then we have a storage system, a compressed air energy system, or called CAES. We have there for air storage, for example, an aquifer, a salt cavern, or an old hard mine. Then we have air and a compressor train. If we compress, we have to cool that, so we have some heat production. So we need power to drive that. It's called PC, compressor power in. Then we have the storage here underground, for example. Then we have the release of the air storage. By releasing, it's cooled, so we have to add some heat, which you can use, for example, also from here. We have the exhaust. Then we have the use of the storage, for example, to drive a turbine, or you can do it in combination with a natural gas. You get a higher efficiency, so you don't drive it by the compressed air alone. You use it in a combination with a gas turbine, use natural gas or distillate or a biogas. Here can have different stages. At the end, the shaft, you have a generator which provides electricity, PG, generator power output. The further abbreviation is HS. This is the hours of storage here. It's related to the PC, the compressor power in. So it's 8 hours. So the compressor has to work for 8 hours on full load to fill up this storage. So we have the wind farm. So we have the rated power of the wind farm at certain wind conditions. We saw it already at the lecture for wind power. It's called a PWF, the wind farm size. Then we have the storage, the plant. You don't have to necessarily use storage only. So we have the CAES plant, and we have, as mentioned before, the underground storage. And at the end, we have the transmission line. It could be fed either directly by the wind farm, by PWF at rated power, or via the CAES plant. And the PT is the transmission line maximum power. In order to save transmission costs, we want to avoid big fluctuations and big peaks there. For this application, we need the CAES to provide baseload power. That's not always the case, but in this case, we want to do optimization is carried out for that case. So for this application, we want to provide baseload power. So the research objectives are the following. What is the optimal wind to CAES system size for baseload power transmission? What is the optimal capacity factor of the transmission lines? How much will such a system cost? And can it be competitive against other baseload systems, for example, nuclear, coal, or natural gas? So the key parameters are the size of the storage system, not only the storage size, but also on the power output relative to the transmission size. So PG from the generator to PT, that's a maximum power of the transmission lines. The CAES compression and generation ratio. So we have the input, the PC, divided by PG, the generator size or the generator power, the relative size of the wind farm, so the power of the wind farm related to the maximum power of the transmission lines, the CAES storage time relative to the wind autocorrelation time. So storage time is HS divided to HA, the autocorrelation time. Then the ratio of turbine speed rating to a resource wind speed.
So it's we rated to the average wind speed. So you know from the lecture about wind turbines, we have here a typical distribution, for example, a Rayleigh or a Weibull distribution. You have the average wind speed, and here you have the rated wind speed. Above this, usually the rated power, the the saturation of the wind power plants are reached, and the power doesn't decrease even if the wind speed, it should be a V for wind speed, and here for the occurrence of that wind speeds. And here you have higher wind speeds. Theoretically, you could have a higher output, but usually at the rated power, you reach the saturation of your wind park or your wind generator, and the actual power doesn't go above that. Then we have some secondary parameters, so secondary of importance. So we have the CAES electricity output to input ratio. So that's the energy, E0 divided by EI. We have the wind turbine array spacing. That's a Midwest, not a big issue. Then we have the Weibull shape parameters, K, you know from the wind lecture, and the wind power density, P wind. So we do a wind farm simulation. So we have the Weibull distribution. Here you see the difference between two K shape vectors. K2 is bigger than K1. So K2 is towards higher wind speeds, a little bit more symmetrical. Then we have the power curve of the wind power. As I mentioned before, if you have even at higher wind speed than the rated power, you come to a point of saturation. Usually this curve goes up by a power of 3 with the wind speed. So for double the wind speed, you have about 8 times the power output. But if you reach the rated power, it just stays as a constant power. Then you have the wind speed time series, as you have here, to correlate it to the Weibull distribution, and you have some autocorrelation time mentioned here, and we have the wind power time series. So if you go above of rated power, you have some losses. So this is a rated power, you can put it lower, so you have more losses, and there's a question where to put the rated power of your wind park. This is a typical wind turbine, a German wind turbine by Enercon. You see here the curve. Here you have the wind speed, and here you have the power output in kilowatt. So you have the maximum here close to 8 megawatt, or 7.5 megawatt. And this reached in the vicinity of 15 meters per second at up height. And you have here the power coefficient, or in other words, the conversion efficiency. You have here the maximum is reached here in the vicinity of 10 meters per second of wind speed, and is close to 50% of conversion efficiency. If you reach the saturation, the conversion efficiency is strictly going down. Here again, we have the CAES model. So as we already discussed, we have the air storage with a number of hours of air storage, considering the power of the compressor, PC. Then we have some losses along the way. So you have the wind farm. It's related to the transmission line capacity. You can provide direct output. The rest, if you produce more than the transmission line capacity, you have to feed it into the compressor. If you have even more, it's spilled power, so you lose that power. Also, even if the compressor would be digesting it, there could be the possibility that the storage is already full, so you cannot use that power either. Then if you release the air storage, you have some losses here, and then you have the turbine with the methane fuel. You have some emissions of carbon dioxide. Then you have the output power here, PG. You can feed it into the transmission lines. If it's still available, if the transmission line is fully blocked by the capacity, you won't release the air storage, so you wouldn't need that. But if there is a lack of electricity and there's no direct output, it would totally depend on the air storage here. And on the way, you have also some transmission losses. and this defines the total system output. So it could be ideally the transmission power, but usually it's a bit smaller than that because you have some times with lower production. So it could be equal or lower than the maximum transmission power. So of the base configuration, first let's talk about the wind resource. You have a shape factor of K is equal to 3. That's really good. In Germany it's only 2, so you have higher wind speeds and a more symmetrical distribution. The average wind speed is 9.6 meters per second, and the energy of the wind, or the energy or the power density, is 500 watt per square meter. It's called class 5 there, but didn't discuss this, but that's not so relevant. And we have an autocorrelation of 5 hours. We have the wind power farm. First, we start with an initial value of 2 times the transmission line power. So this is transmission line power is here 2000 megawatt or 2 gigawatt. So we have here 4 gigawatt here. Spacing is just, we start with 50 d in square. So 50 times the diameter in square. So spacing is 50 d in square. The rated wind speed is 1.4 times the average wind speed. The sizing here, the compressor starts here with the sizing here at 1.7 gigawatts. So it's about 85% of the maximum transmission power. The generator is only half the power of the transmission power. So it's 1 gigawatt. So even the releasing all the power from the storage systems, the transmission line is only used by 50%. So in order to be close to its nominal power, you have to provide direct electricity. Then we have the capacity factor. For example, this is required by the utility. In this case, it's 0.8, so a capacity factor of 80%. If you go to systems without storage in Germany, it's in the vicinity of 20-30%. In very good regions in Europe or the world, it's in the vicinity of 50%. So in order to reach 80%, we have to use the storage facility. Again, just a short repetition about the wind speed distribution, wind frequency distribution. We have here the Weibull formula. So we have K divided by C. K is the so-called shape factor. So in Germany, we have typically 2. Here for this example, in the Midwest of the US, it's 3. So it's really, really good. In Germany, 3 is never reached. Even the best case in the North Sea are lower than that. And we have the so-called scale parameter, which is typically 10 to 15% above the average wind speed of a year. Then we have the actual wind speed divided by the scale parameters to a power of k minus 1. Then we have exponential function of e to a power of minus v divided by c to a power of k. We can also integrate this, so all the power provided, for example, v could be saturation velocity here, so from 0 to v, it's then the integration of that formula, and that is 1 minus exponential function of minus v divided by c to a power of k. Here you see the cases in Germany. As I mentioned here, the shape parameters go only a little bit above 2. 3 is never reached. And if you go to in more inner cities, for example, here Stuttgart, it's only 1.23, this K. The scale parameter, as I mentioned already, it's a little bit 10 to 15% above this average wind speed mentioned here. Here you see the different shape factors. So K, best conditions in Germany, a little bit more than 2. You have this one, but key 1 is just the distribution is very uneven. If you go to key, it's equal to 3. So we have a quite symmetrical distribution. For example, here in this case, around 7 meters per second. K is 2, what's typical in Germany, it's called Rayleigh distribution. So we have here the generating power divided by the transmission power. And we, as a base case, we started with a relation of 0.5. So this is the capacity factor. We have to reach 0.8 due to the utility. So this is relevant for us. And this come here to relation between compressor power and transmission power in the vicinity of, how much is it? Also 0.8. You see the effect of that if you modify PC to PCT. You have here the base case. If you have less compressor power, then your capacity factor will go down by a bit. So we can say as a rule, the capacity factor improves with diminishing returns as either PC divided by T or PG by PT increases. So now we discuss the compressor to generation ratio. So we have here again the power of the generator in relation to the maximum power of the transmission line. This was 0.5 before, and we have here the compressor power in relation to the power of the transmission system. So we have here the capacity factor. This is a line where the capacity factor reaches 0.8. So we have a maximum capacity factor of 85%. Again, the base case here at 0.5. If we increase that, then we increase a little bit CF. If we go lower than that, then we decrease the CF. So for a given CF, that's our case, least configurations appears to lie along the slope line. This is our slope line with an elevation of 1.7. We have a minimal increase in capacity factor if we go above the base case. So if we go above 0.5 from 0.1 to 8. So this doesn't help us because we have the minimum. So we just, you see here the difference. So you double the generator size and only the capacity factor goes up from 80 to 85%. Slope is expected to be controlled by the relation of the power of the wind park in relation to the transmission power and the turbine rating. You have the wind farm parameters. So we have the relation of the size of the wind farm to the transmission capacity. So we have the base case again. So we have a wind farm which is double the size as the rating of the transmission line. So this was 4 gigawatt for the wind park, 2 gigawatt for the transmission line. And if we go lower than that, then we lower also the capacity factor. If we go beyond that, then we increase the capacity factor. That's clear. So if you use more wind turbines, then the possibility that we go below the capacity factor is more seldom, and therefore we increase the capacity factor. So we can say some improvements at larger wind farm size in relation to the transmission capacity we can observe, but most improvement is reached if we are below that standard value that the wind farm has the double size of the transmission ratio. So here, if we would go below that value, for example, if we would have a wind farm in the size of 3 gigawatt only, we would suffer in terms of the capacity factor. Array spacing doesn't play a big role, as we see here. Autocorrelation time. So we have the autocorrelation time. This is our base case here. And so we see that there's no improvement in capacity factor if the storage size is really very much bigger than the autocorrelation time and vice versa. So we don't have any big improvement here. So this is very good if you put the size of storage about equal to the autocorrelation time. We can also do power derating. So we come quicker to a saturation of the wind turbines, and so the wind turbine is more often working at its full power, which is actually derated. So we can do that. So first we see that we have the rated power of a wind turbine at a factor of 1.8 to its average wind speed. So we will lose only 7%. So 7% only, this red part is above the rated wind speed. So we would use all that energy, but it's more fluctuating. If we would derate a bit, for example, if we would go down to 1.4 times the average wind speed, we would lose about 36%. Here it's even more because the higher wind speed contain a lot of more energy. And if we put it one by one, so we lose about 72% here of this area, then the CF would go up, but we would need definitely more wind power plants. So we can say CF increases, but rated power decreases, so more turbines are needed to have the same rated power output of the wind park here. As I mentioned already, as the rated wind speed decreases, a turbine run at rated power or maximum power more often of the time. So we have here the generation of the storage systems versus the turbine rating. So we have here the rated divided by the average wind speed. So most losses we would have at 1, but we have been chosen here a factor of 1.4. And as you see here, we would have a very good capacity factor, but we would require a lot of more wind turbines. Here we have the base case called large storage system. So we have a large relation between a rated wind speed divided by the average wind speed. If we go to an alternative place, we would purchase more wind turbines because they are derated a lot. Then we can save some costs for the storage system. So it's a kind of optimization procedure depending on the costs. So we have the cost difference between the wind turbines and the storage system, which is relevant here. Depending on energy, though there's little change in the capacity factor. The wind resource parameters we see here. So we have the wind resource in watt per square meter. And as we see here, it doesn't really change a lot. Virtually no change in capacity factor over wind intensity from 200 to 1000 watt per square meter. So see on the right picture, you see here the Weibull factor K, and here you have as a parameters the rated versus the average wind speed. So you would have a high capacity factor if you would derate your windmills and buy a lot of them. If you would go to a factor of 1.8 of a V rated towards a V average, you see that the capacity factor is very much lowered. So what you see here with the Weibull factor, so this is not the most relevant parameter. Much more relevant is here this relation V rated divided by V average. So the conclusions are the capacity factor of 80% is achievable for our base case. That means we have the size of the wind park in relation to the transmission power of a factor of 2. We have the generator power divided by the transmission power by 0.5. We have the compression power, a relation to the generation power with a factor of 1.7. We have a storage time of 10 hours, spacing 50 d in square, and we have the rating or V rated divided by V average of 1.4. The base case is somewhat improved by increasing the number of wind turbines or the rated power of the wind park in relation to the transmission line. It is improved also by upscaling the generator power in relation to the transmission power or by array spacing, but possibly they are all more expensive. The optimal storage time should be somewhat larger than the wind autocorrelation time. Part 2, we have comparable capacity factor by reducing the system size of the storage system and rating the turbines lower. So we have to spend more money on the turbines because we derate them.
with a dependence on the capacity factor on the shape factor key, which is coupled to the turbine rating, with capacity factor increasing with K for lower V rate divided by V average and decreasing for higher V rated by V average. And the changing of the energies, the wind power has a little effect on the capacity factor. Thank you very much.